This is it. This is our last problem. This is problem number 3. It doesn't say problem number 3 on it, but it is. It's the one with propionic acid. So let's get right to it. You should be able to do this. You should be able to write the equilibrium constant expression for any of these. Okay, so that means Ka. Here we go. There we go. Ka equals, and of course it's the 1.34 times 10 to the negative fifth. Okay, but it also equals products over reactants. So I take my brackets, meaning concentration, of C3H5O2 minus, like that. Brackets, that's not a bracket, that's like a summation. Okay, all right, I don't know why I can't do that correctly. There we go. This uses the H plus instead of the hydronium ion of H3O plus. It makes no difference to us what they're using. Either one is fine. And that looks like that. So here is our first one. You should be able to do that no problem, no sweat. The next part is the part, of course, where I take my, I hate it when it does that. Hang on. There we go. I'm going to do my ice. To find, if I'm finding pH, that means what I'm finding then is the H plus, and then I'll use my little equation for pH equals the negative log of the hydrogen ion concentration. So let's go through all this business here. Writing this down so that we can H5O2 minus plus H plus. Okay, so what I'm going to do is go through my ice chart. It gives us the starting concentration, has to do that. Give myself a little more room, like this. I'm starting off with 0.265 concentration, 0 and 0, plus X, I get X and X. This is, of course, minus X, and 0.265 minus X. My Ka for this is going to equal then X squared on top divided by 0.265 minus X. You guys know what we can do here. I talk about it all the time. I love the fact I can get rid of that term, which means that all of that is equal 1.34 times 10 to the negative fifth. Okay? Which means I'm going to multiply this times this and get my X squared equals. So I multiply those two to get 3.55 times 10 to the negative 6, which means X equals 1.88 times 10 to the negative 3, which means pH equals the negative log of this number. So pH then equals 2.725. Okay, that's it. I hope there are no questions with that. I hope you got through that pretty easily. That's a very standard problem. Maybe we should just quit while we're ahead and not worry about anymore. Unfortunately, I want to give you guys more experience with working with moles. So let's keep going. I'm going to plow through this. This is going to be probably a pretty long one. So we have a sample of the sodium propionate, which is NaC3H5O2, is added to 50 milliliters of that solution. Assuming that no change in the volume of the solution occurs, calculate each of the following: the concentration of the propionate ion in the solution and the concentration of the H plus. So the first thing I'm going to do is find the number of moles of the NaC3H5O2. That's going to equal, now you guys know this is like, that's going to be a 1, a 3, a 5, and a 2 times 23.0 times 12.0 times 1.0 times 16.0. Okay, when I add all of that up, I should get, now, let me do this, 0.496 grams over 1 times 1 mole of NaC3H5O2 over 96 grams equals. So when I divide those, I should get 5.17 times 10 to the negative third. That's the number of moles NaC3H5O2. Okay, good. So that's just a standard moles, grams to moles calculation. Shouldn't be a problem. Now we're going to divide, of course, by all of this number of moles. You guys know that concentration equals number of moles divided by liters. Moles per liter. The liters I have is now 50 milliliters equals 1, 2, 3 places equals 0.0 liters, like that. Okay, so my molarity then equals 0.103 concentration. Excellent. Good. Let's keep going. The concentration of the H plus ion in the solution. So this now means that we are starting, I'm going to stay on this page here, get myself a little bit more room and switch colors. So this is the answer to I1 right there. Let's move to red and do I2. We're going to start off with C3H5O2 plus C3H5O2 minus. I'm going to start with my concentration of 0.107, 0.103. It's literally right above me there. There we go. For that, I'm going to start with a 0 here, and this is my ice chart, of course. We're doing ice charts all the time now. And we started with 265 for our concentration. That's going to be a minus x. This is going to be a 0.265 minus x. This is going to be a plus x, and this is x and 0.107. Oh my God, what is wrong with me? Seriously, plus x, like that. Okay, now you know, there we go, there are 2 tries. You know that my Ka is 1.34 times 10 to the negative 5th, and you know that what we can do then is we can get rid of, well, here, let's do this. This will be C3H5O2 minus, this is H plus, like that. All of that is over. Like that. So what we're going to do then is I'm going to fill in the 0.107. You know what we can do with this. We can get rid of that times x, all divided by the 0.265. You know that we can get rid of that also. Like that. I love doing that. Okay. Times 10 to the negative 5th, like that. So I'm going to multiply by that, divide by that. That means when I solve for x, I'll write it down here just to make sure everybody's okay. You understand what I'm doing. That's that one. I'm going to multiply by 0.265. I'm going to divide by 0.03, like that. I keep writing the 7. I have no idea why I keep doing that. My x then is going to equal 3.4 times 10 to the negative 5th. It doesn't ask for pH, I don't think. Let's go back up to the top and see what it asks for. Concentration of H plus in the ion solution. Okay, it would be easy to find the concentration of H plus in the ion solution because I just used that, but it doesn't ask for that, so we're going to stop there. Okay, let's stop there. I'll do one more screencast.